Hello, my dear students. Good evening. How are you doing? Okay, I hope you all are having a great day so far. Nice. I'm also having a great day. Thank you for asking. So, my dear students, let me introduce you myself. My name is Vaishali, and I'm your electrical engineering faculty for today's class. Okay, so without wasting any time, or let's get back to our topic of today. So today we will be having a very important topic from point of view of examination, and in gate also it comes. So very important topic, right? So please do concentrate, have a notebook and pen with you all. So we will be starting in today's class, right? So today we will be talking about Laplace transform. Okay, so basically we will be talking about classical method using Laplace in today's class. So please confirm if you are able to see the whiteboard. Yes. So we will be talking about classical method using Laplace. So anybody, have you heard about what is Laplace and what is Laplace transform ever before? No? Okay, fine. So yes, we will be talking in detail about it. First of all, let's understand what is Laplace transform, right? So this Laplace transform is basically used to convert an ordinary differential equation. So we have differential equations, right? So differential equations which are in time domain, we have to convert it into algebraic polynomial in frequency domain. Okay, so what we are doing? We are converting the differential equation in the time domain to from time domain to frequency domain, right? So from time domain, we have to convert it into frequency domain, right? So this will make our calculations easy to understand. Okay, this makes the system easier to manipulate, right? So to take a note of this, so classical method involves two different steps. First is to determine the complementary function, and secondly, determine the arbitrary constant. Okay, so Laplace transform method involves different steps. First step which we have to take is take the Laplace transform of both the side of differential equation. Then we will be applying the appropriate Laplace transform to the derivative terms. Further, we have to solve the resultant algebraic equation to obtain the Laplace transform of the unknown function. And then we will be putting the initial condition into the resultant equation and solve the output variable. Now, why we are doing this? What is the advantage of doing this conversion? So the conversion of an differential equation into algebraic equation of the same order, that is simpler to solve. So our mathematical calculations become simpler, and it gives us an initial condition for free. So to allow the composition of differential equation for control theory, this Laplace transformation is basically done. Okay, now when we are doing this Laplace transform, we have a table, right, to find the transform as well as the inverse Laplace transform. So Laplace transform is denoted by, let me tell you, letter L. Letter L. Okay, so Laplace transform of function of time, say f of t, is defined as L inside the brackets f of t bracket close is equals to, we have to do it in the frequency domain. So f of s. So here we will be taking uppercase f, sorry. F of s. Now we will be doing the integration. So that will be integration from 0 to infinity f of t into e to the power minus st dt. So let's call it equation number 1 for us. So where s is nothing but the complex frequency variable. Okay, noted everybody? And what is S? What, when we are saying this S, what is this S? So S is equals to sigma plus j omega, right? Now, to have Laplace transform of f of t, the original time frequency function, that is ft, must be multiplied by e to the power minus st, and integrated, then it should be integrated from t is equals to 0 to t is equals to infinity. As we can see, this is, we have the formula over here, right? So that is L function of t is equals to f of s. So we have, what we have done, from time domain we have converted into frequency domain, and then the next step is to integrate it from 0 to infinity, right? So here now we will be solving it 0 to infinity. Now also f of t is to be defined for t greater than 0 and t f of t is equals to 0 for t smaller than equals to 0. Understood it till here? Now let's do the inverse Laplace transform. So the inverse Laplace transform L inverse, we write it like this, okay? F of S bracket close is expressed as L inverse f of s, that is from time domain to, now we have to convert it into frequency domain. Sorry, frequency domain to time domain now, right? So inverse Laplace we are doing, that is equals to 1 by 2 pi j integration of sigma 1 minus j to infinity to sigma 1 plus j infinity f of s e to the power st ds. So this is our equation number 2. So here we can see the sigma 1. So what is the sigma 1? So sigma 1 is the real positive quantity. Okay, so here to be noted is the inverse Laplace transform as defined involves a complex integration known as counter integration. What it is known as? Okay, so I hope you have understood this. Do take a note of it. Right. So here, my dear students, you have to make sure that you are understanding how you can do the Laplace transformation. Okay, so let me tell you, when you are doing the Laplace transformation, we got the formula as, let me use my pen. So we have used the formula here. The Laplace transform of any function of ft is given as an expression Lf of t is equals to f of s integration of 0 to infinity function of t e to the power minus st dt, right? So to solve any of the Laplace transform equation, we have a table. Okay, so let's first talk about it. Yes, so these are the formulas to be noted when you have to solve the Laplace transform, right? So from time domain to frequency domain whenever we have to convert. So here you can see the first formula when we have an capacitor, right? And current I. So for converting from time domain to frequency domain, what we have? C is equals to C by S and I is equals to 1 by S. From for t is equals to 1 by S. Okay, so make sure that you learn this table, right? So this will be helping us to solve any type of questions. Noting everybody? So once you are done noting, let me know. We will try solving one question on it. Okay. So let's solve a question on this, right? So see, this is for where f to the power 1 is the integration of function. Okay. So inverse Laplace transform, as we have discussed, the mathematical process of passing for complex variable expression to time expression is called as inverse Laplace. Rotation of it for the inverse Laplace is L to the power minus 1. So L to the power minus 1 function of S is equals to Ft. Differential equation as we have solved for classical method by Laplace transformation method. Okay, so Laplace transform is based on time domain analysis and Laplace transform method is based on time domain analysis. So classical method for solving differential equation becomes quite cumbersome. So therefore, in these cases, we prefer Laplace transform, right? So solving differential equation by Laplace transform involve different steps as we have discussed. Moreover, now let's solve a question on this, right? So let's find the Laplace transform of sine omega t. Okay, so let's do it together. So let's solve it. So sinusoidal function we have. So f of t is equals to sine omega t. So that is equals to e to the power j omega t minus e to the power minus j omega t by 2j. Then we have f of s. So make sure that when we are taking f of s, we have the capital S, right? And f of t as lowercase f, that is equals to integration of 0 to infinity now. So that is, we will be integrating it. So second step, e to the power j omega t minus e to the power minus j omega t. Put it in the brackets. Minus e to the power minus st into dt divided by 2j. Now solve this, convert it into f of s is equals to integrated. So 1 minus j omega t e to the power j omega t minus j omega t, it can be replaced by 2j 1 divided by s minus j omega minus 1 upon s plus j omega. So therefore, solving this, we get f of s is equals to omega upon s square plus omega square. So this is our answer. Okay. So this way we can solve a Laplace transform of sine omega t. Right? So this is how we have the classical method using Laplace. Okay, so let's summarize what we have learned in today's class. First of all, we have learned about the classical method of Laplace transform. So in this, we have understood that what is Laplace transform first in the first case. And in the second case, we have understood how we can solve the questions on it and the table that you have to be learned, prepared for the transformation of Laplace. Okay, so thank you so much for joining. Bye-bye. Take care. Good night.